Assalamualaikum and good day to our respected instructor, TS Muhammad Fadli and everyone present today. When we look at the future of clean energy, we are just looking at massive structures. We are looking at precision engineering. Today, representing Group 1, we are proud to present Wind Turbine, a 3D CAD exploration. This project isn't just about drawing lines, it is a comprehensive, high fidelity 3D design and modeling execution using AutoCAD, tailored specifically for our computer aided design course, BNR 27402. Let us take you through how we brought this complex mechanical system to life. Behind this advanced CAD simulation is a dedicated team from the BNE program. This engineering feat was conceptualized and modeled by Akmal Izzat bin Mohammad Nazri, Umar Lutfi bin Afifudden, Mohammad Adam Iqbal bin Mohammad Najib, Mohammad Farish Fikri bin Wahid Anwar, and myself, Mohammad Akib bin Abdul Rahman. Under the invaluable guidance of our instructor, TS Muhammad Fadli bin Abdul Razak, we push the boundaries of AutoCAD to ensure absolute dimensional accuracy and structural integrity in our model. Now, let's look at how a horizontal axis wind turbine actually converts wind into electricity. It comes down to three main steps. First, aerodynamic lift. When wind flows across the specially designed airfoil blades, it creates a lifting force. This force is what makes the rotor start to spin. Second, mechanical transmission. Next, that rotational movement is captured by the rotor and goes straight into the main shaft and gear system. Third, electromagnetic induction. Finally, the generator takes over. The mechanical motion rotates the magnetic field inside, which successfully generates electrical current. So, from just a simple breeze, we get clean, usable energy through smart engineering. This is all from me. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Umar Lutfi bin Afifudden. My matrix number is CN240258. Today, I want to discuss the critical role of engineering precision in modern renewable energy, specifically focusing on horizontal axis wind turbine, also known as HAWT. If you look at the left side of this slide, we see where every great engineering project begins a conceptual sketch. While sketches are excellent for capturing initial ideas, relying on inaccurate or loose technical drawings downstream introduces severe risk. Inconsistencies in the design phase inevitably ripple outward, leading to costly construction errors, inefficient assembly on site, and spiraling maintenance costs over the turbine's life cycle. To solve this, our objective as visualized on the right is to bridge the gap between concept and reality by engineering a precise one-to-one scale, highly detailed 3D digital model using AutoCAD. We ensure absolute clarity in geometric visualization and seamless structural integration before a single piece of steel is ever fabricated. Okay, now let's break down exactly what components make up this massive structure. Okay, to understand the engineering complexity, we need to look at the structural anatomy of a standard industrial horizontal axis turbine. The exploded view highlights how critical components must seamlessly interact under extreme mechanical loads. Okay, first, the 100-meter tower. Starting at the foundation, this massive column elevates the turbine to high altitudes. This is crucial because wind speeds are stronger and significantly more consistent the higher you go, while the tower itself must provide a rock-solid structural stability. Okay, next, the 60-meter rotor blades. Moving to the rotor assembly, this blade utilizes a highly specific aerodynamic profile designed to maximize lift and optimize wind energy capture. The nacelle and hub, the hub securely connects these rotating blades to main shaft, transferring that aerodynamic force directly into the nacelle. The nacelle acts as the main housing unit, protecting the delicate mechanical and the electrical system from harsh environmental elements. And finally, the generator. Inside the nacelle sits the generator, the core conversion system of the entire asset. It takes that mechanical rotational energy and transforms it into a grid-ready electricity. When you look at these components isolated like this, it becomes clear that even a millimeter of misalignment could throw the entire system out of balance. Because of the sheer physical scale of this asset, traditional scaling method can introduce math errors. That is why we utilize AutoCAD's infinite canvas to draft a strict one-to-one scale using real-world dimensions. This ensures exact compatibility during manufacturing. To put this into perspective, look at the scale comparison on the right. When you are dealing with a machine that stands 100 meter tall with a 60-meter blades rivaling the height of of a commercial high-rise building, the tolerances are incredibly unforgiving. Minor geometric or angular errors at the root of a blade will compound exponentially over 60-meter length, leading to a massive aerodynamic imbalance or a catastrophic structural failures. By creating a one-to-one digital twin, we can completely validate the aerodynamic alignment, stress point, and geometric tolerance in the digital space. This rigorous verification process guarantees that the system will perform flawlessly. Thank you, and now I'm open. Thank you, and now I will let my group members continue.
Hi, good evening. My name is Umar with AN240116. So, on the seventh slide is a systematic CAD workflow. The first one, we are doing research analysis, studying HAWT structures, aerodynamic performance, and load distribution. The second one is concept sketching. We are doing planning preparation and component arrangement for task delegation. On the third one, we are doing on AutoCAD application, 3D part modeling utilizing specialized CAD tools, extrusion for the tower, and sweep or revolve function for the rotor blades. And lastly, we are doing assembly and integration, verifying positioning, spatial alignment, and structural symmetry of all components. So next, we are on the eighth slide, which is a structural organization via AutoCAD layering. So on the first layer, we are blade geometry layer, continuous solid line, defining the naked oil foil. Profile is optimized for wind energy conversion. Second, which is tower layer, continuous lines mapping, height dimension, and the tapered design for wind load efficiency. On the third layer is Nacelle layer, main housing documentation for the gearbox, control system, and generator. And on the last layer, foundation base layer, provide structural anchoring details, which is the layer uh, that are controlling the height. On the ninth slide, it's a navigating digital environments. Model is paper space. On the model space, which is a design engine, function, main 3D drawing and editing environment. Scale, we are using infinite canvas at 1-to-1 real world size. For the output, structural modeling, geometry optimization, and spatial alignment of components. Versus paper space documentation, function, presentation, layout, and specification marking. Scale, scale appropriately for viewing and printing. Output, orthographic projections. X loaded assembly views and precise dimensional annotation.
So, Assalamualaikum and hi. Nama saya Akmal Izzat bin Nazri from Matrix AN2401. So, in this slide, saya akan explain kita focus on internal mechanical designs, which is blade hub and gear integration. So, this hub was designed with three blades, mounting points positioned at 120 degree each interval to balance rotation. Then the gearbox mechanism was modeled to precise gear to spacing to achieve smooth power transmission. These mechanical components are essential for transferring rotational energy from the blades to the generator. And then we move on to the next slide, which is the hardware limits. Modeling the AC motor. So one of the challenging challenge we encountered was modeling, especially modeling the generator of AC motor. It is because it has various components to implement. So I do like within not now, but then I do like it takes 1 day to complete the outer, the middle, and the smaller part of the motor. These components contains many interaction, include features such as shaft, casings, and mounting interference. So the competing axis and increased file size and processing requirements, causing the software lag and performance issue. It is because I'm using 2027 AutoCAD, so that is something suspicious uh, uh, at, at that model. So to overcome this, we optimize our drafting techniques and carefully manage model details to maintain system steady.
So from this slide, from digital wireframes to realistic rendering. So first of all, after completing the 3D model, we decide to do a realistic renderings. So the material and texture will apply to the tower blades and nacelle housing to simulate real wind turbine. So you can see here, this is the real turbine with our realistic renderings using Notebook LM. AutoCAD rendering tools transform the wireframe model into a visual realistic representation. This improves visualization and helps in communicate to the finance design more effectively. That's all for me. Thank you.
Hello, Assalamualaikum warahmatullahi wabarakatuh. My name is Mohammad Iqbal Umar Najib. My metric number is AN240141. So today I will bentak so today I will talk about milestone and digital collaboration. So as you guys see, this slide show the project timeline and the collaboration process among the team members throughout the project. The first milestone was on 15 May 2026, where we conduct an online meeting through Google Meet to discuss the project proposal and develop the initial concept design. Next, on 20 May 2026, the team coordinate through WhatsApp to delegate tasks and plan the individual component that would be designed by each member. After that, on 5 June 2026, we held a face-to-face discussion to review the design component and verify the physical assembly of the complete wind turbine structure. This stage ensured that all parts were compatible and correctly positioned. And finally, on 15 June 2026, we conduct the final error checking and drawing review through Google Meet. And during this stage, we identify and correct any remaining issue before finalizing the design. So overall, the combination of an online communication platform and face-to-face meeting allow the team to collaborate effectively, maintain project progress, and complete the digital twin model successfully within the planned schedule. So right now, as shown on this slide, the development process starts with a conceptual sketch of the wind turbine nacelle. This initial sketch provides the foundation for the design and help us visualize the overall structure. The sketch was then converted into a detailed AutoCAD engineering, drawing with precise dimension and technical specification. This step ensures that the model accurately represents the actual component. And finally, the design was transformed into a realistic 3D model, creating a digital twin that closely resembles the physical wind turbine component. Through this process, we demonstrate how AutoCAD technology can be used to improve design accuracy, reduce potential construction error, and support the development of more efficient and sustainable renewable energy system. That's all from me. Thank you.
That is all from our group. Thank you for your attention.